Welcome to this NPTEL course on Advanced Prestress Concrete Design. Today we are moving into this module 2. In this module, we are going to talk about the losses in prestress, focusing on immediate losses that includes elastic shortening, anchorage slip and friction losses. After going through this video, the student should be able to explain the various sectional properties that will be used in the calculations of the losses in prestress and estimate the elastic shortening loss in both pre-tension as well as post-tension members and estimate the friction and anchorage losses in post-tension members, and also should be able to establish the force variation diagram. Now, these are the sectional properties that you can see. Various schematics have been given in this slide, and you can see that if you are talking only about concrete area only, then we denote that as AC. That means you are excluding the area that is occupied by the steel. Here in this case it is the prestress in steel. Here that we are calling that as AP, which is your prestressing steel. Now, this AC plus AP will give you this overall area, the entire cross section area, which we call that as simply A, right. Now, the modular ratio of the steel and concrete are going to be different. If I convert the steel into an equivalent concrete area, then the total area becomes transformed sectional area. And you can see here, this is also in this schematic, we are able to see a typical box girder segment, and if you calculate the CG of this concrete area, then your CGC, this is basically center of gravity of concrete, right. And for the steel, again, only for steel, if you measure the reference axis is at the bottom, and then if you calculate your CG for the steel, then we denote that as CGS, which is CG of steel, only steel, right. So, now the distance between the CGC and CGS is the eccentricity of the prestressing tendon or total prestressing force. Prestressing force. So, this eccentricity is what will be used for calculating the stresses. So, in this way you calculate CGC separately from a reference axis, CGS separately from reference axis. The distance between them is your eccentricity of the applied prestressing force. So, these are the notations that we will be using in the calculations of losses in the coming slides. Now, let us understand why we need to be concerned about losses in prestress. I think in the introduction video also we have explained the early failures in the prestress concrete structures were mainly due to inaccurate prediction of prestress loss, right. So, now in this part of the module we are going to talk about the immediate or short term losses. In the next part of the module, we will be talking about long term losses, right. Now, when you apply prestressing force, typically that will be the jacking force will be the force that you actually apply initially on the prestressing cable. Then that will reduce to P service, which is the prestressing force that exists while the member is under service stage, right. The service period, depending upon whether you are looking at 1 year or 2 year or 3 year, your prestressing force that is existing in the member will differ depending upon at what time that you are calculating the or what you are looking at the prestressing force. This is mainly because the creep, shrinkage and relaxation will actually start reducing the prestressing force over a period of time. So, we have to account for that. Depending upon the time at which we are looking at it, the effect of creep, shrinkage and relaxation will be different, and that we have to account for calculating the what is the pre-stressing force that is existing at the service time where we are doing the calculation, right. So, now if you look at this service immediate after immediate losses, you understand that the P service is definitely going to be less than Pj, which is your jacking force, right, jacking force, okay. And the same member over a period of time, because of the effect of creep, shrinkage and relaxation, P service will start reducing and then it will become P long term, which is definitely going to be less than the P service that we looked at it, and which is also going to be less than your Pj, which is your initial jacking force or jacking stress that we gave to the tendon. Now, this is what it is, the P final, P final, let us say you are doing the calculation at the end of 5 years or 6 years. This is the pre-stressing force that is going to be existing, and that is definitely going to be lesser than your P service, which were there in the initial periods, and it is definitely going to be less than the initial jacking force that you had initially applied on the pre-stressing tendon. And you can see that the sagging also you can find over a period of time, because of the effect of creep and shrinkage, the pre-stressing force will reduce, and because of which the beneficial effects of pre-stressing will come down, and then you may end up with this kind of cracks. That is what it is given in this particular schematic. Now, why we should be concerned about losses, right? So, we need to, depending upon again which time that you are evaluating the stresses or the condition of the element that we have designed, we have to account for both immediate or short term losses as well as long term losses, right. Now, when we do that, sometimes if you do the overestimation of the losses, it can lead to high pre-stressing force in the initial design. Let us say that you are saying that you will have 20 or 25% of loss that will happen in pre-stressing force, then you account for that by putting more cables or applying more pre-stressing force. So, if you do not estimate it and if you overestimate the losses, then you will end up putting more pre-stressing force that can cause excessive camber like this. This is what we are seeing here. In that process, what we are going to do, we can also crack the element for this case at the top, which is a simply supported case here. So, when I apply pre-stressing at the bottom, I am going to develop tension at the top. So, if I do estimate the losses on the higher side, then to compensate that, I will put more pre-stressing. So, when you do more pre-stressing, you may accidentally crack at the tension side, or it may also have a higher camber. So, this is again overestimation of losses will lead to this effect. Now, on the other hand, if you are underestimating the losses, and then what will you do? You will put less pre-stressing strand and less pre-stressing force. Then what will happen is, under service stage, you may have cracks for this like this at the bottom on the tension side. So, the pre-stressing is not adequate, right. So, both overestimation of the losses and underestimation of losses is not good. So, we need to have a realistic estimation of pre-stressing loss. In fact, an exact determination of the pre-stressing loss is not feasible all the time. Sometimes, most of the time in design applications, we will assume a lump sum loss estimate. So, what is the meaning of lump sum loss? That we will discuss in the coming slides. So, the point what we are trying to see here is, there are multiple factors that will influence the pre-stressing loss. So, exact determination of pre-stressing loss will be difficult. So, we need to keep that fact in mind while we account for the losses. Now, let us move on. In losses, as we have discussed, we are going to have two categories. One is the immediate loss, another one is the time dependent loss, right. In immediate loss, we have three important losses that can happen. One is from the elastic shortening of concrete. So, when you apply pre-stress, concrete is going to get squeezed, right. In that process, you will also lose the stretching that you are initially giving to the strand. So, that loss is called elastic shortening. We will discuss about that. Then we have friction losses. This friction and anchorage loss, this will come in post tensioned system. Post tension system. Okay. In the introductory module, we talked about pre-tensioning, post-tensioning and so on. In post-tensioning, we have a duct inside a concrete element. After the concrete is hardened, then we push the strand or tendon through the duct and then we stress them. So, while you stress it, you are going to have friction forces that will develop, and also the anchorage at the anchorage ends, there will be the slip that will happen. Because of that, the pre-stressing force, there will be reduction. So, that happens only in post-tension system. But elastic shortening can happen both in pre-tension and post-tension system, more so in pre-tension systems, that we will discuss in the coming slide. Now, with respect to time dependent losses, as the name says, it is function of time. So, depending upon at what time that you are doing the calculation, the effect of these phenomena like concrete, it creeps over a period of time, and depending upon what time that you are looking at, the amount of creep will change, right. Similarly, shrinkage also, concrete shrinks, we know that, but depending upon at what time that you are looking at it from the time of casting, that amount of shrinkage will change, and it will cumulatively it will increase over a period of time, that we have studied it in the previous parts of the module, that we have to account for that. Then relaxation is related to pre-stressing steel. Okay. This is a phenomena related to steel. These two phenomena are related to concrete. So, concrete undergoes creep and shrinkage, and pre-stressing steel undergoes relaxation. So, we have to account for all of these effects. Now, we will see how the elastic shortening occurs in a pre-stress beam. And you can see this is a schematic of a beam, and you see this red color element, that is basically your so this red color element is basically your pre-stressing steel, right. And you can see here that initially we stretch the tendon or the pre-stressing steel to some strain. Okay. So, this is the length of the tendon before stretching. So, that means from here to all the way here is your initial length of the pre-stressing cable, and then we have stretched by some strain magnitude. Okay. This is the initial strain that we have given, which is epsilon p j, right, and that creates a pre-stressing force p j, right. And now, how do we get the p j? P j is nothing but A p multiplied by E p times epsilon p j. So, strain multiplied by elastic modulus will give me stress, stress multiplied by the pre-stressing area will give me the force. So, this is the initial condition. So, p j is nothing but the initial pre-stressing force that we have given because of the stretching of the pre-stressing cable by a strain magnitude of epsilon p j. Now, when I release this pre-stressing, for example, let us say in this case of a pre-tensioning system, when I cut the strand, then the stress will get transferred from steel to concrete. So, when that happens, because now I am applying a force to the concrete, finally it will reach a value of P naught. So, at this stage, due to the application of P naught, now the concrete will undergo some strain, which is your epsilon c, which is the strain that is happening because of the elastic shortening. Now, how much will be the strain that will be left? Initially, we had epsilon p j. Now, the concrete has also shrunk by epsilon c. So, the net strain that is available in the pre-stressing steel is epsilon p naught, that we have to so epsilon p naught will be equal to epsilon p j minus epsilon c. Now, these are the notations that we have, Pj is the initial prestressing force in the tendon, and epsilon Pj is the initial strain in the prestressing tendon, and P naught is the prestressing force in the tendon after elastic shortening losses. So, that is what we are in fact trying to find out, what would be the P naught, and epsilon P naught will be the strain in the tendon after elastic shortening losses, and epsilon 3 is the strain in the concrete due to elastic shortening of the tendon, right. Now, let us see, we have seen this. So, now what is epsilon Pg? The definition, as we can see, the strain is nothing but stress divided by elastic modulus EP, right. So, now how do we get the stress? Stress is nothing but the force divided by the area of your prestressing steel. So, that is what we have got it here, which is Pj divided by AP into EP. Now, what is epsilon P naught? That again the same strand, now it is subjected to force of P naught. So, the strain that is left in the strand is going to be P naught by AP divided by EP, right. So, this is the initial force. After the transfer, the force what we have is P naught, right. So, when you see that epsilon C, that is the elastic shortening, the strain due to elastic shortening, right, which is difference, which is epsilon Pg is the initial strain minus epsilon P naught, and now this is your epsilon C, that is the elastic shortening strain. Now, what is the force that is lost or the stress that is lost is basically how much strain that particular steel has lost. Now, how much is the strain that particular steel has lost, which is nothing but epsilon Pj minus epsilon P naught. So, we call that as delta epsilon P naught. So, that differential strain that is lost multiplied by the elastic modulus of the prestressing steel will give me the stress that is lost, because stress is nothing but strain multiplied by elastic modulus. So, EP into delta epsilon P will give me the stress that is lost. Now, what is delta epsilon P? That is what we have said. This is nothing but your epsilon C, right. So, this is epsilon C. So, in finally, the force or the stress loss due to elastic shortening can be given in terms of EP into epsilon C, right. Now, this can be further simplified by converting. Now, how can I write epsilon C? Epsilon C is a strain in the concrete. Now, the strain in the concrete can be written as epsilon C can be written as stress in the concrete divided by elastic modulus of the concrete. Now, if I put that for expression for epsilon C, then delta Fp will become EP into Fc by Ec. Now, EP by Ec, we know that it is modular ratio. So, modular ratio, we know that the definition for modular ratio is EP by Ec, and modulus of elasticity of prestressing steel is 2 into 10 to the power of 5 megapascal, and concrete, depending upon the compressive strength, it is typically taken as 5000 square root of FCK as per IS 456, right. So, you can calculate these different modular ratios. So, in this way also I can calculate the stress that is lost due to elastic shortening is nothing but modular ratio multiplied by the stress in the concrete. Or if you want to talk in terms of strain, the stress lost due to elastic shortening is nothing but elastic modulus of the prestressing steel, which is EP multiplied by epsilon C, right. They are all one and the same. Okay. Now that we have understood what is elastic shortening, let us look at in various scenarios how do we calculate this elastic shortening loss, right. So, let us first look at pre-tensioned axial members, okay, and let us look at now what happens on how to calculate the elastic shortening, right. So, again we have explained this previously. This is the original length of the member at the transfer of prestress. When you just in pre-tension case, as you know that before you pour the concrete, the tendons are stretched and you pour concrete. Once the concrete hardens to a certain extent, then you go ahead and cut the strand. At that time, basically the transfer of prestress happens. Now, at that time when I am cutting the strand, this is how the length of the member at the time of transfer of prestress. And we know that the initial force is Pj, and we have already discussed this, right. Now, once you do the transfer, then the member shortens and then it becomes P naught, and this is what we are trying to find out. So, the difference between Pj minus P naught is the force that is lost, the prestress force that is lost because of the shortening that is happening in the concrete, right. Now, how do we calculate that? I think we have already seen this. Delta Fp is nothing but m into Fc. Now, the question is, how do you calculate Fc? Fc, we know that at this, if you look at this particular case, Fc is nothing but the force that is being transferred to the concrete is P naught. So, P naught by AC will give me the Fc. Now, but P naught is what we are trying to find out, right. So, but what we know is how much initially we applied. Pj we know, but P naught we do not know. That is what we are trying to find out, right. So, then how do I get that? So, we need to find somehow what is the relationship between P naught and Pj, and then use that Pj for calculating the loss due to elastic shortening. Now, we can prove that this P naught by AC is equal to Pj by AT. Now, if you remember, AC is the concrete area only and AT is the transformed area of the cross section, right. And you can calculate the transformed area for any cross section, but then for simplicity you can also show that this m into Pj by AT will be approximately same as that of m divided by Pg by A. Now, what is A? A is just the cross sectional area, the total cross sectional area, we call that as A. So, you know Pj, you know A. So, quickly you can calculate your delta Fp in the form of modular ratio times Pj by A, because it is very simple, right. We know Pj and we know cross section area, but we do not know what is P naught, right. But so, that is the reason we are trying to calculate the stress loss due to elastic shortening in terms of the initial applied force and the cross section area. We can also prove that P naught by AC is equal to Pj by AT. Now, let us see how do we do that. It is a very simple derivation. So, again going from the first principle, we know the strain in the concrete is epsilon Pj minus epsilon P naught. As you know, epsilon Pj is the initial stretching that I have given and epsilon P naught is the final strain that is left in the strand. The difference is the strain that is lost because the concrete is shortened, right. So, now again from this we can also express what is the definition for strain. Strain is nothing but stress divided by elastic modulus. Now, the stress is this, P naught by AC is your stress in the concrete, divided by EC will give me epsilon C. Similarly, epsilon Pj is nothing but stress in the pre-stressing steel divided by EP, and then the final thing is also this is epsilon P naught is nothing but stress divided by stress due to P naught divided by EP. So, from here we get this simple definition. Then we can see that if by a little bit of rearranging the terms, for example, if I take this P naught, the entire term, if I take it to the left side, then you will have P naught can be taken out, then you will have 1 P naught into 1 by AC into EC plus 1 by AP into EP will be equal to Pj by AP into EP. Now, this also again when you do further simplifications, you will find that this will become, so if I multiply everything by EP, then it will become EP by, so this entire thing if I multiply by EP, so here it will become EP, here also will become EP, and this will get cancelled, right, and this EP is also, you know, when I multiply that, this and this will get cancelled. So, you find that this EP by EC is nothing but your modular ratio, then it will become m by AC plus 1 by AP will be equal to Pj by AP. So, in a way what we are telling here is there is a relationship that we are trying to find out from relating P naught and Pj, because we don't know P naught, that's what we are trying to find out. So, I have to express all the stress laws in terms of the initial pre-stressing force, right. So, that is what we are trying to see. So, though we know that epsilon c is P naught by AC divided by EC, I have to find the relationship between P naught and Pj, right. So, that is what we are trying to say. So, if you do the simplification, we can express that P naught by AC is equal to Pj by M into AP plus AC. Now, what is this? And you know that this is nothing but transformed sectional area. So, we can say that P naught by AC is equal to Pg by AT, which is your transformed sectional area. So, you can see that this is equivalent to this. So, I can find out the delta Fp directly in terms of Pj and AT. This is the actual definition. Now, that also further we said this is nearly equal to Pj by just A. Okay. We can also show through example that the differences are very, very negligible if I just use the jacking force and the cross sectional area of the section. Okay. Now, let us see pre-tension bending members. Now, in a bending member, we know that the cable profile is not going to be linear, it is going to be mostly it is going to be parabolic, right. Sometimes you can have also linear profile if you have a point load that is coming, that we will discuss when we talk about equivalent loads analysis, stress analysis concepts. Now, you can see that in a pre-tension member, you are going to have a cable will be at an eccentricity, and you can see here this is the eccentricity of the cable, because this is your CGC and this is your CGS. The difference between them is nothing but your eccentricity of the cable. That is what we have marked in this schematic. Now, when I transfer the pre-stress, what will happen is the beam will camber upward, because now what we are applying is not only pre-stressing force, also we are applying a moment at the two ends when you transfer, because P into E is a pre-stressing moment that you apply, because of which the beam will curve upward, right. So, now typically this such, let us say this beam is also having some self weight, and you know that self weight is also going to be uniformly distributed along the length of the member. So, this is the total weight that you will have. Now, what would be the stress in the concrete at the level of pre-stressing cable? Because we as per your definition, we know that the elastic shortening is function of your epsilon c, right. To calculate my epsilon c, for example, delta Fp, we know that it is nothing but modular ratio times the stress in the concrete. Now, how do we calculate the stress in the concrete? And you can see for this particular case, beam is subjected to, let us say, right, it is subjected to some pre-stressing force Pj. In addition to that, there is also a moment that you are applying, right. So, what kind of moment that we are applying? We are pushing it upward, right. So, it is going to create this kind of a moment, which is MP, which is equal to P into eccentricity E, right. So, or in that way I will write Pj, maybe I should write equal to Pj times E, which is your force, right. So, that is what we have. Let us take that compression as negative, compression stress as a negative. So, if I am calculating the stress at this particular cross, now if you look at, let us say, at one particular cross section that I am taking, I am going to have this kind of a cross section I am going to have, and then let us say this is your CG and this is where your pre-stressing cable is, right. So, I am calculating the stress at this particular fiber, right. Let us say I am calculating at this level, right. So, what would be the stress? Now, you see here the Pj is also acting and pre-stressing moment is also acting. So, if I take compression as negative, right, then there is a axial force which is Pj, that is going to create a compressive stress of minus Pj by A, because compression I am taking negative, and there is a moment. At that moment is going to induce compression again at the level of the pre-stressing cable. That moment is Pj into E, and what is Y here? Now Y, we are calculating Y, which is equal to E, the eccentricity of the cable itself. So that is Y here. So M by I into Y will give you the stress that is happening from applied pre-stressing moment. So that I get it here. In addition to that, this member is also subjected to some self-weight, right. The self-weight moment is creating again and again by I into E. So this is the net stress when I add all these components. There is an axial component, there is a pre-stressing moment component. In addition to that, there is also self-weight that is acting. So all these three things, when I add it up, and I will get the net stress. Now this applied self-weight moment, it is going to create tension. That is the reason I have created positive here. The rest both of them will create compression. That's the reason we have taken negative here, right. So when you add all of them, then you get your net concrete stress at the level of pre-stressing steel. Now elastic shortening is happening, right. You are calculating the strain in the concrete at the level of pre-stressing steel, right. So that is what we are doing here. Okay, now here, and as we have seen, MSW is the moment at the midspan, and E is the eccentricity of the pre-stressing, and I is your moment of area of the cross section, right. So in this way, you can calculate my stress in the concrete, and typically the amount of pre-stress will be applied in such a way that the strain values will be small. So the concrete will still be in the linear elastic regime. If you look at this now, if you want to do the now here in this case, the moment is also going to vary. So you have to do the calculation along the entire length of the member, and you can get your average loss in the pre-stressing force, right. Here we did the calculation only for one cross section. This Pj by A and the pre-stressing moment is not going to change. However, moment due to the self-weight will change depending on, for example, you see here this is only supported here. So it is going to be moment at the midspan is going to be WL square by 8. But however, at the supports you are going to have 0 moment. So depending upon that, your again stress in the concrete will change, because the self-weight is also now coming into picture for the straight cable profile. But if you have again parabolic cable profile, then things will be changing, right. So that again we have to keep it in mind.